Hello? Yeah, I guess it's working. Cool. Hello, everyone, and welcome to, oh, sorry, maybe.
Now it's on, yes. Thanks. So yes, next up we have Simone Ponzio from ARM, and who is going to talk about practical methods for functional verification. So Simone's background is in electronic engineering with a focus on digital design. And for the past 4 years, he has been working as a verification engineer at ARM, primarily focusing on CPU verification. And today he is going to be sharing some insights with us that he has learned over the years. Thank you. Simone, go ahead.
So, yeah, good morning, everyone. Today I would like to start by sharing a personal story. And it's about me here at CERN, working on my master thesis project. Back then, I was working on this small piece of logic that I had to implement, and that had to be integrated into a data acquisition system. At some point, I completed the scratch of the design, and I realized, oh, I need to verify this. How do I do that? At that point, I was only aware of simulation. And so I took my design, put that into a simulator, and threw some direct tests at it. Looking back, that was probably not the best approach. But that's not really the point. The point is that I thought that verification was about making things run. But no, verification is about building confidence in your design. And this is really the motivation behind this pitch. So design is growing more complex and bigger. And we need to figure out how to deal with that. So in the next 20 minutes, I would like to go through the practical method we have to face design complexity and other challenges, and hopefully build some confidence in our design. So the agenda of today, I'll try to introduce some of the common verification methodology, and that hopefully are available for you. And I'll introduce some of what I think are the functional verification challenges of nowadays. And then we'll try to dig down in each of them and try to understand how to tackle those. And there will be some key takeaways and open to the Q&A session. So common verification methodology. Hopefully most of you at least are familiar with simulation-based verification. This is quite of a common way to do verification, not because it's simple, but because it's pretty available. Usually that's based on the concept of building a test bench around your design. And what you do really is you write a piece of software. And this piece of software is made of some components that you use to drive and monitor signals. And then you need to write some stimulus, you need to write some checkers, and hopefully some coverage. And then you put everything into your simulator and you run it. Then we have formal verification. So formal verification is quite different. This is because you need to rely quite a lot on something that is called a formal tool. And this tool is able to take your design as an input, convert or elaborate your design into a mathematical model, and then is also able to generate all the combination of the inputs. And you might be wondering, well, what is left for me? Well, you actually have a lot to do, because you need to write something that is called properties. Properties are nothing else than rules that relate signals. Let's say something like, if signal A is 1 and signal B is 1, then signal C should be 0. That's just a dummy example. And these properties can be either constraints, meaning they constrain the inputs, so you cannot have all the possible combination, but only the valid combinations of inputs. And they behave like assertions. And when they behave like assertions, they are there to check the correctness of your design. And then you have emulation acceleration. This is a bit of a different word, because here you are on real hardware, or almost. Emulation is a bit of a word in between. And acceleration can be on FPGA, can be on ASIC. And really the difference is that here you're going real fast. So you can execute real workloads. And the heartbeat though, is that you don't have full visibility of your design. Most of the time, you only have a bunch of probes that you put into, and you can observe those. So it can be quite tricky to debug. If I had to compare formal verification with simulation-based verification, they are very different in the way in which you can use them. Meaning that simulation will allow you to explore a specific part of the state space of your design, basically, and those are the tests that you're writing. And formal verification will try to formally prove mathematically your design. This is not always possible, unfortunately. Otherwise, we will blindly go and use formal verification the whole time. But it's pretty good always exploring the first stages of the state space. So we have this amazing set of tools. Why do we need so many? Because verification is not just complex, it's getting more complex. And here are a few of what I consider being the biggest challenges we have in nowadays verification. I would like to start with the one in the middle, that is incomplete or evolving specification. No one likes to write documentation. It's boring, we know that. And, but the problem is that when we need to verify something, we need to understand it. Otherwise, how can we verify that? And what happens if the verification is incomplete or keeps changing? How can we face that? So we will try to answer this question. Another problem is design complexity. So design grows bigger and more complex, and this is because we want more performance, we want more features, and that means that the state space of this design is growing. And it just means that it's harder and harder to hit all those corner cases and be sure that our design is working in all the possible states. And the last bit is verification closure. That's another pain. And this try to answer the question, when can I say I'm done with my verification? When can I say verification is completed? This is good. Let's start by looking at design complexity. So one way I really like to tackle this problem is by modular verification. And by modular verification, I mean, I like to take my design and breaking it down as much as I can in smaller bits, and then verify those bits independently. So let's call those, like usually large design have big hierarchies, deep and wide. And so what you do, you take this hierarchy and you say, okay, can I isolate some bits of this hierarchy? And if I can probably write a verification environment around it. So what I'm really telling you is to write a verification environment around all these, let's call them units, but that doesn't mean that you don't need to write a verification environment around the whole design. Because if you don't do that, you're not sure that the whole design is going to work. So you might be wondering, Simone, you're asking me to write a test bench around each unit and then a test bench around the whole thing. It's a lot more work. And I will say, yes, but. And we move to the second point. If you do it smart enough, you can reuse a lot of the work you did at unit level and bring it up at higher verification levels. So at the end, you're not doing everything from scratch every time. You're just reusing a lot of what you did at unit level. For example, you might be writing some monitors, agent, let's call them, to look at the output of your design and some checkers to check the output of one of those subunits. Then that bit will go at higher verification level, and you will reuse it. And so you will have confidence that that part of your design is working both at unit level and at system level. The third part is constrained random testing with functional coverage. So direct stimulus are not enough, mostly when the design is big and complex. You cannot just keep writing tests. It's too complicated. You will end up writing so many, and then something might change. You really want to leverage on randomization. And randomization by itself might cause you to end up in some illegal cases. So cases in which the combination of the inputs are not legal. And so you won't constrain those stimulus. But when you constrain, the risk is that you over-constrain the stimulus. Over-constraining the stimulus means that you are basically allowing your randomization to do the job, but then you are limiting it so much that you are not exploring some real use cases. And that's why we need functional coverage. Functional coverage will tell us that. But we'll get to functional coverage in more details later. And the last bit is use formal verification if you can. Formal verification can have a very big reward on investment. The investment is big as well, because putting like bringing up a formal verification environment can be quite time-consuming. And the other nice thing about formal verification that is not just going to provide a full proof, at least in the early stages of your design, but it will also complete altogether with the simulation base. Because if you find a bug in formal that you didn't find with your stimulus, it means that some of your stimulus are missing, or maybe some checkers. And yeah, probably what I really want to say here is that don't limit yourself to one verification methodology. That might not be enough. Incomplete or evolving specification. The first thing I like to do when I'm not sure about the specification is to plan ahead. Because if I'm not sure what I need to do, I need at least to have a plan on what I can forecast. And one way to do that is writing a document that is called a verification plan. The verification plan is just a collection of stimulus, checkers, and coverage for each feature. So you know exactly what you want to do, or at least you have a rough idea of what you want to do. And the more specific you can be, of course, the better it is. And it will give you a kickstart, let's say. Second point is collaboration. Collaborate closely with designers. Of course, if you're not writing the design. But yeah, if you're not writing the design, there is someone that is writing it, and you want to talk to them. And mostly, if the specification is incomplete, you want to try to figure out with them what is the design supposed to do in some cases. Usually, just by discussing one use case of a feature, you can figure out up to 80% of that feature, statistically speaking. There is a risk in the collaboration with the designers, and this risk is called common mode failure. Common mode failure is when both you, the verification engineer, and the designer, that might be, unfortunately, the same person sometimes, end up doing the same assumption on the specification. So assumptions are natural. Everyone will make them. But if we can separate those assumptions, we can build something more reliable. And then now we move to a bit of a more technical part. That is, use assertions, like leaving spec. Assertion in your design can behave really like leaving specification, because specification might keep evolving or might be incomplete. But when you write a property into the design, that property must be coherent with the design behavior. So whenever the spec gets updates, you update the design and you update also the property. And if you don't update one of the two, of course, everything will fail. And this is very useful because it gives you the security that you have something that behaves really like a piece of specification in your design. And also properties will help you to constrain the stimulus, because they will tell you what is valid and what is not valid if they are placed on the inputs. And the last bit is design for change. So, and here I mean design your verification environment for change. So be able to reuse as much as you can, write modular code. Verification closure. This is quite funny because it sounds like it's all about coverage. There is coverage, 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 and then something else. So let's start from functional coverage. Functional coverage is quite useful because you try to write some things that are called cover groups, cover points, and they basically tell you, hey, is this event happening? Is this functional event happening? And you want that event to happen. But then the problem of functional coverage is that you're writing it, and you're human, so you might forget to write something. So you will never have a complete set of functional coverage. That's why we need more type of coverage. And code coverage is one that is very helpful. Code coverage is there telling you if you executed all the pieces of code of your design. And I'm simplifying this a lot because code coverage is many things. Can be line coverage, can be expression coverage, can be branch coverage. It's many things. But you really want to balance these two together and try to make a good use of code coverage. The third, to be honest, that's part of code coverage, but I like to move it out because it's called toggle coverage, and it's pretty useful and simple. You might want to look at toggle coverage because toggle coverage tells you if all the input and output of a given module are toggling. And if some of them are not, you might be wondering, oh, maybe I'm missing something here, or a piece of my design is dead. Statistical coverage. This is quite of a separate beast, because statistical coverage, it's complex to bring up. You basically need to collect events, put them somewhere, probably a database, because you are collecting those events while simulation is running. And then you want to plot them over time or space. A simple example of statistical coverage might be a heat map of a memory. So you want to figure out how much of that memory I am occupying or reading, whatever, over time and over space and the frequency. So why is statistical coverage useful? This is useful to help you understand if your stimulus are biased towards something. Going back to the example of the heat map, maybe you are always allocating the first addresses of the memory and never allocating, or very rarely allocating the one in the middle. And you don't want to do that. You maybe want to have more a uniform distribution of the allocation inside your memory. And the last bit is bug trend. So to be sure that you are close to completing verification, you want to see that bug trend, that is basically the number of bugs coming from the design over time, going down. And if it approaches 0, it means, hey, maybe I'm almost completed. And so verification closure is a bit a balance between coverage and bug trend. So let's close it here. Key takeaways. Design is growing more complex, and we cannot do much about it. And we cannot just write more tests. We might think to try to break down the design and verify the pieces of it. We can try to use random stimulus. We can try to use several verification methodologies. Specs will always evolve. We cannot control that. And what we can do is we can plan ahead. We can try to use assertions and as living specification. Very useful. Verification closure. This is not just about hitting 100% coverage. Please do write coverage, it's important. But it's about being able to justify why you're done. So you need to look at coverage, sure. You need to look at the bug trend. But mostly you need to have confidence that what you're doing is working. And yeah, I would like to close by saying that when I wrote my first verification environment here at CERN, I only had a bunch of tests and hope. But I realized that hope isn't the way. Verification is a process, is a mindset. And as we get better at it, we can have more confidence in whatever we build. Thank you. Any question?
Thank you. Hands up. Yes, go ahead.
Hi, very nice presentation.
Thank you.
I have learned about formal verification at the university, and I did it there. But
Sorry,
I've never.
can you speak up?
Yes, sorry. I've learned about formal verification at the university. I did it there, but I've never used it in a real-world commercial project. So what is the largest design you ever formally verified?
So I personally don't work on formal verification on the day-to-day base, but in the industry, formal verification is used on quite large designs. I know that there is that concept that if the design is too large, formal verification just doesn't work. And it depends what you want to do with formal verification, because if you want to use formal verification to formally prove something, sure, a large design is always going to be incomplete, because you will never be able to go through all the state space unless, because it's about resources, right? It's very hard to go through all the state space. It's too large. But you can get up to informal verification. They are called bounds. It's basically the number of cycles that you go through, and you can formally verify your design. And so the way in which it's very useful, also in the case of large designs, is that first, you are sure that up to, I don't know, bound X, your design is working, 100%, all the combinations. Two, you will likely find bugs in those 100+ bounds. And those bugs are for probably some scenarios that you are able to figure out by looking at the formal waves. And then what you might want to do, you want to try to reproduce that in simulation. Because if you are able to reproduce that in simulation, it means that you might find other similar bugs that are much deeper in the time line. And so basically, one is completing the other. So formal verification per se, it's super useful for these reasons, I believe. Also on larger designs.
Okay, so you're always doing partial formal verification. So not the full design, but a part of the design exploration states.
Not necessarily partial formal verification, because if you have, when I talk about breaking down your design, right, and doing verification only around subset of your design, let's call them units again. If a unit is very suitable for formal verification, you might only want to do formal verification because you might find yourself in the situation in which you are able to fully prove that piece of design. And that gives you quite a lot of confidence. Something else to consider, though, is that formal verification is limited. The capability of formal verification is limited by what you write. If you don't write enough properties, if you don't write enough assertion, I mean, one assertion will tick, and what do you know? If the rest is going to work or not. Yeah, that's it.
Okay. Thank you.
Yeah, thank you.
Yes, go ahead.
So you said everybody makes different assumptions. So don't make any assumption based on this question, on how I work. If we wanted to start with verification, where should we? What do you suggest, especially with formal verification? Where do you suggest we should start from?
That's a good question. So, yeah, it can be intimidating. I understand that. So like, oh, it's complex. There is this formal tool that do all this magic. I don't know. I don't understand it. I don't understand it, but I use it. So first, you need to get the tool. You get the tool. You learn how to use it. You need to learn how to write properties. Probably that's the hard bit, apart from joking. It's very hard to write properties because the way in which you need to think in formal verification is quite different from the way you think when you do verification, like simulation-based verification. Usually you need to think kind of the other way around. It's like, if this doesn't break, what I need to do, kind of, because you need to build these properties, and the way to build them can be quite tricky. But yeah, I would tell you, like, yeah, focus probably on learning more about how to write these properties and all the syntax of these properties that can be very complex, can be quite complex, because you can write properties for very complex sequences of events. And those are usually the most powerful ones, because they show you what happened over periods of time, not just like in this moment, I know that this signal must be 1, this signal must be 0, and and then this other signal must be, I don't know, 1 again. So yeah, it's like like learning formal, it's a process. Of course, it's like practice will help, tutorial will help, but yeah.
Thank you.
Yeah, no worries.
I have maybe a related question.
Yeah.
Do you have any favorite resources that you would recommend for learning for any of these approaches?
Well, nowadays Google offers everything, but let me think. I did some trainings, of course, mostly on simulation-based verification. The other I learned a bit with experience. If you want to learn specific things like, for example, UVM, that is a standard in industry for simulation, you might want to go for a training or look for a training. Again, there is a lot of material online. And what I believe is like, when you know what you want to learn, it's easier, and it's like, and then you find a lot of material around. The problem is like knowing what you want to learn most of the time.
Sometimes the problem is also just knowing what is the right word to Google, right?
Yeah, correct. And you can just ask around. Like, people might know.
Do we have more questions? Yes, go ahead.
So this is maybe related to Francesco's question. I guess you work here at CERN, no? You said before, and you maybe know that typically we work in very small teams where the same person writes the RTL design and is also in charge for the verification. Yeah. So I was wondering how, so if we take a relatively large design, how long would it take to implement this and try to stay in time with our deadlines for, I don't know, commissioning of our experiment?
Yeah, I understand. Resources is always a concern, of course. Yeah, it's not obvious. It depends what you want to do. But the main idea is that if you don't dedicate enough time to the verification, it's really hard to say that whatever you're doing works. Because maybe then you put it on your FPGA, you run that couple of tests, it does work. But then when it goes in production, stuff happens, right? And that's a pretty tough position where to be. Like your design breaks in production, what do you do? It's a tough position. But how do you handle that? How do you handle the pressure? You probably need to balance the time that you spend doing your design and the time that you spend doing your verification. That would be like probably the first approach that I would look at. When you break down your design, maybe instead of breaking down your design after you completed your design, you want to do that on the go. Meaning, okay, I need to build this complex design. It is made of 3 modules because I plan it that way. I bring up a module 1, and I realize that I can do some simple verification because that's not too complex. Maybe I can even use formal. Let me try to write some properties around it. And you do that, and then you move to the others. One thing I didn't mention. So when you do your design, what I always recommend to do, because I've seen it doing, and I think it's super, super useful, it's write a lot of assertions in it. Embed a lot of assertions in it, as many as you can. It's like you think about a use case, put an assertion. It's like you think it's like, oh, I know that these 2 signals are related in this way. Write an assertion. Because when you will write your test bench and simulate it, it will tell you exactly what it's failing. And this is one case in which being the designer of the verification, it's helpful because what is failing, it's exactly what you know, because you know those signals, while the verification engineer would say, oh, something is failing. It's inside the design. I have no idea. I'm not going to open it. I promise. You will go into that and look at it and know how to fix it. So that's probably something that can help you to speed it up a bit.
Thank you.
No worries.
Any more questions? You have another one? OK.
If there is time. So we had some discussion during the rest of the conference about many tools that write HLS code, machine learning based. I was wondering how would you integrate this kind of, I guess, from the perspective of an electronic engineer, like black box in the design and in functional verification.
So you're asking about machine learning mostly, or?
Like if we have a machine learning algorithm, neural network that we we start from a PyTorch, and then we have an HLS, and then we have an IP. So yeah, there should be some way to integrate this in a verification framework, let's say.
Well, I mean, I'm not sure I got fully your question, but I don't know if you're mostly asking about what I think is the role of AI into this, or?
No, I think he's asking, because this is my typical question. It's, you have this block that has code inside, but you don't really know what the code is. But still you are using it because it's generated by external tools that tell you, this is this BDT or this machine learning. And then you have this block in your design. How do you verify it? How do you?
I see. I mean, thank you. Sorry, I didn't get it at the beginning. So yeah, usually, I mean, that's usually the way in which you should do verification. You shouldn't know what it's inside the block. You should only know the specification of the block. Because when you know what it's inside the block, you are influenced. And so you write your stimulus and your checkers thinking of, oh, this is in the block, so I want to look at that detail now. And you might think, oh, but this is great. You're testing exactly what you know it's inside. No, because it's like you're making assumption at that point. And you are missing on maybe something that is more architectural, if you figure out what if I'm clear. The best case scenario to do your work, if you're a verification engineer, is that when you have your spec perfectly explained, you have no idea of how the design is behaving inside, and then you write your test bench. Your test bench might fail miserably because you didn't understand something, or, and so you made a mistake, or it's failing miserably because the design is miserable. And that's the case in which you're right.
So that's actually the ideal case when you don't know what's inside.
Correct. That's what you really want. You don't really want to know what is inside. And when I work with designers, sometimes they want to explain to me. It's like, yeah, no, because this is working this way. I'm always, no. Don't tell me that. I don't want to hear that. Because otherwise, you're going to influence the way in which I'll do verification. Yeah. I hope that helps.
OK, thank you. Let's thank our speaker again.
Thank you very much.
And finally.
I'm going to leave it to you.